Thanks for coming out to our talk. Our talk is Finding Bad Acorns, and if you were in this room for the Comcast talk, the guy said, we are fighting to have the most awkward title. I think we might have them beat. So, bad acorns in this context would be fraudsters. We're trying to find fraudsters. I hope that was clear. So just a quick introduction. I'm Andrew, and I've been working with Capital One for coming on 4 years, and in the fraud space, 3. You can find me on LinkedIn, and my random fact is that I like to play a lot of Dungeons and Dragons.
Hi, I'm Jeff Sharpe. I've been working for Capital One for just short of 2 years, most of the time with Andrew. I'm also on LinkedIn, like everybody else. My icon there is a slice of bread, because I actually semi-well-known around the office for being a big fan of baking.
So together we are a group. We're part of a group of teams called the Forest, hence the logo. And we've been working on building out a platform on Kubernetes for real-time fraud decisioning. We're aiming to bring in a lot of use cases onto this platform. We've been running in production since in September of 2017, and right now we have 3 use cases with hopefully a lot more to come. So our talk today is going to be first about our journey developing this fraud platform and on Kubernetes, and how we're using Flink on that platform. And for the second part of our talk, we'll do a deep dive in how our Flink application looks, what the job graph looks like, and if you see the Lambda on the squirrel's head, how we're using that as a entry point. So, in fraud, our first users are, of course, our customers, and there's constantly this sense of balance between stopping fraud versus providing a good experience for our customers. Example, if you're a customer and you open your bank account and you find that someone else has all emptied it, not great. At the same time, if you haven't done anything wrong and all your funds are locked out and you can't access them, that also is not a good experience. You see this, this is just a common trend we see in fraud. That goes for our fraud operators as well. Like, we only have a limited number of people who can call our customers to check whether the transactions are fraud or not, and we have a lot more customers than that. So it's just not realistic for us to overload our operators. So we have to do this balance between how many transactions we tell them to follow up on. So our next users would be our data scientists and our data analysts. One of the premier things that we have to worry about or directives that we were provided, is to build a platform that will empower our data scientists and data analysts to quickly look at our data, ingest it in an easy-to-consume format, and be able to turn around models quickly. So that's just our primary user. And I saw this slide from the keynote, and I hadn't seen it laid out so nicely. So thanks to them for showing me this slide. When our product owners and our business partners ask us to build us this platform, they're really asking us to do all this. So that's sort of what our platform is built, what the directives we're trying to build out with our platform. Sorry. And lastly, because this is a fraud platform, and it would be nothing without the fraud use cases on it. It would just be a bunch of machines that aren't doing anything unless we had the engineers who have to develop on this. So we need to build a platform where it's easy for them to build their fraud applications. And that goes to the point, if you're a developer and you're tasked with building out a fraud application, and in the platform everything's already there, I think that would make a pretty great developer experience. So without further ado, this is our architecture. It's very simple, but I didn't want you to show the internal diagram with all the acronyms. So, but this is pretty much the basic ideology behind this platform. You provide it data, you do some magic with Kubernetes and Flink, and then you decide whether it's fraud or not, and you restrict the account or call the customer or something like that. So right now we're running on 15 EC2 instances, and for the Kubernetes portion, we're running about 200 pods. So while I can't talk, while I didn't show you the diagram with all the acronyms and stuff, I can talk about the technology we're using on this platform. First of all, that's a lot. That's not even all the technology we're using on the platform. The first one that's missing is Zookeeper, of course, but I really didn't like how their icon looked. It's just a picture of a Zookeeper. And we also have like Redis cache as well. So the first two are the basis of our Kafka architecture. We very liberally use Kafka as our messaging bus throughout the platform, be it talking between NiFi or Flink to Flink. We potentially use it a little bit too liberally, but it's been pretty good to us, and so far, not too many complaints for that level. We also have NiFi as one of the ways we grab data from different sources in our company. We have Minio and Istio to handle the Kubernetes layer platform communications. We have your standard EFK stack for monitoring logs. And we have a combination of, we have a combination of Influx. We're transitioning to Prometheus and Grafana for monitoring capabilities and fraud dashboards. Here's an example of our dashboard monitoring Flink task managers. It's a little bit hard to see, but the one on the bottom shows us when a task manager dies or not. So you get this really clean visual of when that happens. And so the last three, Zeppelin, Pachyderm, and Drill, are really geared towards the data scientist portion that I talked about earlier. Drill does the queries on S3 or whatever data source we have on the platform. Zeppelin provides a notebook form for them. And Pachyderm helps with the refit pipeline when we need to train our models more quickly. So developing on Kubernetes with all this technology has been a real challenge, but very rewarding. So I'm just going to do a quick glance at the pros and cons. The pros, the community's support for Docker and Kubernetes is really amazing. I think a lot of people are trying to do Kubernetes right now, so a lot of the issues you'll find are, if not solved, at least well documented. We've had some pretty good experience with the resiliency and aspect of Kubernetes in that we've had task managers just go into unknown state or die, and Kubernetes is able to bring that back up, and it works very well with Flink's HA capabilities, and we won't see too much downtime, and the task managers that were spun up from Kubernetes will be able to connect those task managers back to the job, and we won't see much downtime after they recover from the checkpoint. So on that note, it's also easy to tear it down and bring back up, which as a developer I find is really helpful when I really screw things up. Just delete, 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 and it'll just come back up. And of course the main reason why we use Kubernetes is to utilize our resources and just distribute them as efficiently as we can. So the con side for Kubernetes, you have to maintain your own Kubernetes solution, which is a task in itself. We have basically the equivalent of 3 teams managing the infrastructure to make sure we're our downtime is never too long. And if you don't configure, so I would say Kubernetes out of the box really is limited in that you really need to make sure your configurations are set up correctly. Otherwise, you'll face a lot of problems like blast radius. So there's this concept of namespacing in Kubernetes that says that your namespace aren't supposed to overlap, or when one crashes, it doesn't affect the others. But if you don't configure your resource limits correctly, we've seen situations where one Flink job on one Flink cluster just tears down the entire, or pretty much makes the entire Kubernetes cluster in an unknown state. And there's a lot of, because you're using all this pretty cutting edge stuff, there's a lot of edge cases that you'll run into, and it'll be very hard to find what the underlying issue is. The one I remember specifically is we were having nodes come down, and we really didn't know why. The logs didn't say anything. And it wasn't until someone went on the specific nodes and looked at the Docker logs, because of the resource limits being hit, the nodes were crashing, and the Docker logs never made it to the Kubernetes logs. So that was just one example of the things that happen when you combine all these things. So because this is Flink forward, I'll talk a little bit about how we use Flink on Kubernetes. The way we do it is actually the way we found to be the best is you actually run multiple Flink clusters on Kubernetes. So we have tenants, or each use case will tell us their desired resources, and then we'll provision them a Flink cluster. That could be we usually use one job manager, because as I said previously, when you're combining all this tech, it's kind of weird. We found that if you're using two job managers, there was this weird state when one job manager came down and the other job manager was trying to restore from Zookeeper, and it was getting this really old jobs. It was really weird. So we're going with one job manager and many task managers for each Flink cluster, and many Flink clusters to a Kubernetes cluster. So we're using RocksDB as our backend, and we checkpoint and savepoint to S3, and we deploy our jobs through a service that we've deployed on top of Kubernetes that calls the Flink API. So now we're going to talk about the specific use case that me and Jeff are most familiar with that we developed on the platform. Just a reminder, this is the defense at the teller. So when a customer comes to the teller, this is a defense that we developed and improved that will tell us whether the customer cashing the check or withdrawing cash is trying to do a fraudulent transaction or not. And our SLA is not super strict, but at the same time, you don't want them to just be waiting there forever, yelling at the computer. So for this problem, previously our previous defense didn't have access to all the customer transactions or all the customer activity that we know of. So that's something we aim to improve with this fraud defense. So the problem is that we have two legacy batch data streams, one from the rest of Capital One, right? All these historical transactions, all this customer activity that he does. And we also have a data stream directly from the branch, which is the transaction that the customer is doing at that moment. So we need to calculate features, and then we need to apply the model, and we need to respond in a reasonable time. So our solution was to, our first attempt at the solution, I should say, was to do everything in Flink as a monolith sort of, and take advantage of Flink connected streams for the historical stream as well as the teller stream. So this is what our DAG looks like in Flink right now, or I should say a job graph looks like. On the top we have NiFi writing to the Kafka consumer, Kafka topic for the customer transactions. And then on the bottom we have a Lambda endpoint on AWS hitting the Kafka topic for the teller transactions. We connect those two streams, and then we do a keybuy for parallelism, and we have some custom windowing that Jeff will talk about. And then, yeah, we'll actually talk about all of these in sequence. So the first one I'm going to talk about is the green one highlighted there, the Lambda, and why and how it performs on Flink, and whether you guys might want to use it or not. And it turns out Lambda was a pretty good fit for our use case, and it worked pretty well for the teller use case. The quick pros: it's cheap, it's not a lot of code. You just have your Lambda handler, that's it, and there's no infrastructure to handle, right? The scalability and availability are free. They come, as a managed service from Lambda. And deployments, my favorite part about Lambda as a entry point is the deployments. Green, blue deployments on Lambda are really a breeze with aliasing. You can deploy both Lambdas, and when you're doing your deployment, you can just switch the tag to use the deployment that you want to be live. So some cons, or pseudo cons, is that it's not truly stateless. That can be an advantage with the second one, which is startup time. You can take advantage, because it's not stateless, you can have your Lambda container stay open and not take up that full startup time. But at the same time, if you don't configure it correctly, because it's still alive when you're killing these connections, some weird interactions can happen. So I put not truly stateless as a con as well. With that, I'm going to turn it over to Jeff.
Mm-hmm. So we're going to go into a little bit more of the details of exactly how this is set up. One of the more interesting parts about this, we are actually dealing with quite a bit of state. This is dealing with bank transactions, not shockingly. And so while we're not quite at Netflix levels of state, we do have quite a bit. I will say over 100 days, and we'll say that's probably sufficient. In this case, we're showing one of the examples of the windows that we do deal with within this particular application. This is a 90-day window. It's supposed to be storing 90 days worth of transactions for a given customer. In order to store something like 90 days of transactions for every single customer who might suddenly decide to walk up to one of these tellers, that is a large amount of state. I think, what was our last number? 150 gig? Does that seem unreasonable?
Yeah, sure.
Okay. That was easy negotiation. So it's a lot of state. And if we actually would store windows specifically for all of the different things that we're looking at, it would eat up a lot more state. And we actually tried that, and it caused some pretty bad stability problems. So we have some customized windows that we've created. These are custom windows. They're implemented actually as keyed value state that we retrieve. These are not normally the Flink native windows. We populate these as part of the DAG that was up here earlier. In this case, we kind of show one of the ways we're optimizing here. So we have a 90-day window stored as value state. We also have a desire for a 30-day window and things like 90-day windows that are only storing some transactions. So in this case, we're storing just that one 90-day window, and then we're going to provide virtual views of the 30-day window and another virtual view of a filtered window. We can actually create these virtual views dynamically as we are calculating features. Another good example, we have this window that does not have a good name at all. I don't even remember what we tried to call it. Here it's referred to as the most recent beyond 24 hours window. If you try to implement this in any sort of normal way, this is a very simple definition that says, I want the one transaction which is older than 24 hours, but otherwise the most recent. In this case, that transaction might be from 25 hours, or it might be from 140 days. But we want to be able to have that in a window. There was no good solution to this. This was actually causing a bunch of stability problems when we tried to do it any normal way. So in this case, we have a very customized window that just keeps track of a one-day offset, and then whatever the most recent was past that. The result in this of doing some of these optimizations actually turned an application that was unwieldy to the point of instability down to something that's actually really reliable. So that's building up our windows, and that is actually probably the bulk of our application. That's where a lot of the, I guess, most important work gets done, because those windows become the basis of reality for everything else that we're about to do. This is where we get to the data scientists. They come in and do their magic. We have an issue which apparently is not uncommon here. We're primarily a Java development team, as most of the development teams in the company are. However, data scientists are more comfortable in Python. We obviously want to use Flink. Flink doesn't operate natively in Python. So in this case, we did some work, and we've built up a Jython library that acts as an adapter. So this lets us implement each of the features as individual Python files. The data scientists for this particular application actually wrote 95% of all of the features themselves. We wrote a couple other ones just to prove that it could be done. And those run within the Flink application. They operate via Jython as if they were Java code. And we had this actually running without nearly as much effort as I thought that we were going to. The result is that you end up with this enriched data stream that passes through Jython, generates all of these features. Bonus point, those features are generated in parallel, which is not something that you can normally do with Python. Second bonus here is that we were able to actually force all of those features to go through normal GITFLOW. So when those data scientists are coding up their features, each individual file, it gets tracked individually. We have Git history for each one of them, and we can actually go back through any point in time, and if somebody asks us, hey, on March 2nd, what was the value of this feature? Git can go and tell us exactly what this is. We actually produce a separate Maven artifact for all of the features so that we can easily track down what everything is. Also, not shocking, the point of all these features in Windows is indeed to apply machine learning models, because everybody loves machine learning. So this is exactly what you'd think it would be. We throw a whole bunch of features at some model, and it's going to generate our model score. So on the slide here, we've got H2O, TensorFlow, whatever, special call out to Selden. We don't actually have anything that uses Selden, we just really like it, and we'd like to actually start using it. One of the main points here is that, specifically with Flink, there's no limitation on what we can use. I think we've got some prototypes that have already used TensorFlow, but nothing in production. Currently, we're using H2O. In all cases, these just are artifacts that are handed to us. Data scientists produce them. It'd be nice to get to the point where we can produce them actually within this application. But for now, we're pretty happy with where this goes. Obviously, the model score ends up being the primary output of the whole app. We pass that downstream to actually make decisions about what we're going to do. I'll hand this back to Andrew, and he'll go over where we're going to be taking it from there.
So this guy is the logo. Well, so internally, our application for the teller use case is called Squirrel. So this logo that I stole from Amazon AWS seems pretty apt. He's a squirrel with a lambda on it. That's basically our application. But there's something wrong with him that we didn't realize initially. The problem is that when you're combining these two streams and they're both sending in transactions, the way that we were seeing a back pressure to the transactions, like our teller transactions were coming in, and for some reason they were coming in late. So the culprit. Oh shoot. Oops.
Now we're
sorry.
Way off the rails.
All right. The culprit. All right. There was a preview. I'm sorry. But the culprit ended up being connected streams. So the teller transactions have a real-time SLA, and the way connected streams works with Flink is that when all the transactions come in, they do some internal queuing. And so what we were saying is that the transactions that were coming from the customer stream were actually backlogging, causing some back pressure with our transactions that really needed to respond quickly. So the solution, if you've been to any software development conference recently, to break up the monolith. And to not only break up the monolith, but break up the monolith Flink app into smaller queryable state apps, and sort of view Flink apps as functions. So rather than squirrel, now we have chipmunks. And the job graph looks fairly similar, except it's split across multiple Flink apps now. So Alvin is our first Flink app that we're going to talk about, and he's basically, all he's going to do is he's going to take a data stream, key by some field, and calculate the features, and he's just going to sit there. And so we're going to have a lot of Alvins, basically, or a scurry of Alvins, if you will. And they will be working on all the data streams and sort of act as like a feature store for other applications to access. And then we'll have Theodore. So in our example with the teller, Alvin would be listening on the customer transaction stream, and he would be doing his calculations and just exposing them via queryable state. So Theodore, because he's the chubbier one, he does a little bit more work. He takes the transactions from the teller. He does the same keying and windowing that we talked about before. But when it comes to calculating the features, he asks Alvin for the features that Alvin's calculated on his side. So, and then he puts it on a topic, intermediary Kafka topic. Like I said at the beginning, we maybe use Kafka too liberally, but we use it as a messaging bus even between Flink apps. And the reason why we split Simon down there up is because right now we're just using the H2O model from the jar, but we could easily replace that with Selden, or one of the examples over there, as like a container that just we pass our features and he gives us a response. Yeah, so the Alvins act as a feature store. We're really trying to, as a platform, we're really trying to allow different use cases to use the same features or have access to the same features. So while previously everything had to be contained in one app, multiple use cases would be able to use the feature store that results from Alvin and queryable state. So the performance of queryable state so far has been pretty good in our use cases. It's been around 100, 150 milliseconds max, so that's not too bad. Okay, so that's pretty much what we did for our use case. This is just summing up how we felt about Flink in general. We use connected streams. We really like key state, and the checkpointing, safe pointing features have been really nice. Queryable state is something we just started using for the chipmunks that you just saw previously, and it's been working out pretty well. So I would love to say, because we're at a Flink Forward conference, that it's been a seamless ride, but obviously not so much, or some hiccups. The big one that got us is, here's a warning to people using Flink: make sure you keep your Flink version updated, because we ran into an issue in those Jira tickets where when our backend, our checkpointing backend, in our case S3, went down. You may not think S3 goes down a lot, but when it does, a lot of people get angry. So what happened in this when S3 went down is that Flink in 1.3.1 would assume that the checkpoints were corrupt and then just delete them from Zookeeper. So we would just lose our state, and while the applications would restore, they wouldn't have any of our windows. So obviously, we were on 1.3.1. Obviously, the next patch was 1.3.3. We missed it by, just a bare amount. So another thing we would like to see is keyed source functions. We already, prior to the Flink applications, we already partition our data on the Kafka layer. We already eat up our cost there. So we really would like to see a way to use those Kafka keys to get a keyed source function, so we can take advantage of checkpointing and save pointing. One of the mailing lists suggested us to use operator state, but we wouldn't get checkpointing and save pointing that we want. And then we had some issues with Kafka offsets when we were doing replays. Something that you might not think of when you're doing a replay. This is an edge case since we're connecting two streams. But when you take a save point, the Flink will take the offset that it's stored in the save point, regardless of the group name that you're using, and use that as a starting point. And it will overwrite, for the most part. There's probably a place where we're supposed to call the consumer set offset that we're not doing correctly. But even though we called consumer set offset in the main function, we were seeing that the save point was overwriting it. So that's something that would not necessarily be clear. So that pretty much that's pretty much our talk. If you have any questions about the fraud defense platform that we're developing, or the Flink use case that we developed, we'd be happy to take them.
So you're using one job manager in your
Yes.
cluster. So in case of failure, there will be downtime, right? I mean, in case of failure, so you'll get an alert and then you'll go and start it, or what?
So when the job manager, you're asking what happens when the job manager dies?
Yeah.
So actually, honestly, since we've moved from 2 job managers to 1 job manager per cluster, we actually haven't seen that situation happen too often. But the task managers, I think what we've seen, I can't remember, when the job manager comes back,
We've had the job manager fail a couple of times.
And it comes back.
Yeah, job manager is fine.
Kubernetes.
Task manager is fine. Yeah, job manager, once it's died, because you don't have any HA enabled, right?
Yeah.
I think the easy answer is that it's one of those problems that Kubernetes solves for us.
Yeah.
Since we've only got a single job manager, if the job manager fails, then Kubernetes will bring back the entire group, which means it'll kill off the task managers, it'll clean up the job manager, it'll bring up a brand new set, everything should come back from checkpoint.
But you have to resume with the same previous checkpoint. That and all is already taken care by Kubernetes?
Yeah, so at least when the task managers die, we've seen that when it comes back up, it's able to register with the job manager again.
Yeah.
For the job manager, we haven't seen it in a while.
Okay.
So.
No, it has been a while. Obviously, that's a pretty destructive thing when it happens, and so I think the only times we've really had that caused was pretty aggressively fixed.
Yeah. Yeah, the other thing is the state. Usually you have 150 GB, the state size, right?
I think for this app, I think that was probably like the high end of what we reached. I'd like to think that it normally stays lower than that, but I think that's a decent estimate.
Yeah, so can you tell me how many task managers you are running for that on that cluster?
Yeah, so for this particular use case, it's running with another app, but it's five task managers to our job manager for that particular cluster.
Okay. And you are not using that like the Netflix model where you create a Uber checkpoint and pushing it, or you are using just default configuration like?
No, we actually, there's quite a bit of tuning actually that went into figuring out what to do for checkpoint timings. I guess one of the lessons I think we kind of hope that everybody eventually learned, we've been trying to teach the other teams about this too, that you do kind of need to go through checkpoint testing to see what is appropriate for each individual app. So even different apps on the same cluster, we do use different checkpointing strategies. So we went through several rounds of different checkpoint settings to try to find which one we thought was going to be the most effective. It's always a set of trade-offs.
Yeah, we are using like the entropy methods that they mentioned. We're not quite doing 21 terabytes in 27 minutes, but
just short of that.
Yeah.
Somewhere.
Okay, thanks.
In back.
Or in the back. Several.
So what limitations did you run into using Jython? Because my experience in the past is like you get some Python code and it works, and then you try running it in Jython and it just doesn't work.
I've made jokes about the fact that I'm not able to do any of these presentations about Jython without somebody bringing up the, hey, but what about this limitation of Jython? And the quick answer is, yeah, there are a bunch of limitations on Jython. And the first one that always gets asked is, can I use NumPy and SciPy? And the quick answer is, no, you can't. There are ways of getting them to work in a JVM. They are pretty gross. I don't actually want to do it inside of a Flink job. However, I've tried to make the data scientists happy by giving them a suitably nice development environment to work with. And basically anything that they might want to use with NumPy, you can implement that in Java, or you can use a Java library and expose that to Jython. And usually it's close enough that you can give data scientists an API that they're happy with. We're not able to get to the point where we can say that a data scientist can just write, a block of code in their Jupyter notebook and move it immediately to one of these features. But it's close enough that it makes them happy. We are heavily regulated, and our regulation office, they've looked at the code and they're happy with it. So it's enough that everybody feels more comfortable than they would be if they had to copy the code into Java.
Just a follow-up on that one, probably. What has been your experience with Zeppelin, and why Zeppelin? Why not just use Jupyter? That's the first question. And second one is
question that Andrew wants to answer.
Second question would be in the deployment model. Why go with Kubernetes? Why not Mesos? Because I saw another presentation. Mesos seems to be nicely integrating with Flink, especially with the Flip 6. So I'm just curious, what's your experience been?
Why want me to take the first one and you take the second? I can give you the easy answer. So why Zeppelin instead of Jupyter? And I think the easy answer was that Zeppelin had nice integrations with Apache Drill. And we had a decent amount of data that was sitting in various different locations. And the ability to query across those with Drill was, I guess, its main driving feature.
As far as
Zeppelin works with that, we have had some issues with it, but I think that was really the pairing that drove us.
Yeah, and in terms of how Notebook's good, I've used it myself. It's not bad. So, I mean. Oh no.
Yeah.
We're not using Zeppelin as a Flink interpreter. The platform has developed some custom interpreters for the data sources we're querying, but no, we don't have a Flink interpreter or anything.
Ultimately, Zeppelin is, I guess, considered downstream. Zeppelin is what we expect to be used to interpret the results of the Flink jobs.
Yeah, it's a tool that the data scientists can use to take a look at the score transactions and see if their features are being calculated correctly, right? As far as why Kubernetes, we have a lot. I'll go back to the slide where we have a ton of stuff. So we are pretty on board on the container side, and we have a lot of things running. So we want to run Kubernetes is a pretty good environment to run all these things and run any container that we might want to have.
Yeah, I mean, it might end up becoming a religious argument, but I think in this case we kind of just lean toward
we're too deep. We're too deep now.
Yeah, it's too late. The decision's been made.
Any other question?
Yeah, you talked about keyed source being an issue. There's actually a fix for it in 8571 that you could look at.
What was the issue?
You said that if the source is already keyed, you don't want to do a key by again.
Yeah.
So Stefan Richter has a fix for it, and it's in 8571. And we worked with it, and at Netflix we've backported it to 1.4.
Okay.
There's still some work needs to be done around key group assignment, but as long as you have your hashing functions matching, you should be able to use that.
Okay.
Awesome.
Well,
we'll get to work on 1.4 then.
Blame Fabian on that a little bit. I asked him that question, and he said, "Not that I know of."
This is pretty recent, though. It's just a month and a half old.
Anyway, over here.
Have you given any thoughts to, like with GDPR coming out, and maybe you don't have a lot of European customers, but like the kinds of considerations for the infrastructure to address, especially like on the explainability side for certain use cases with GDPR, like how you might go about addressing it or are as you start.
Is that a regulatory thing, GDPR?
Yeah.
Yeah, so for the moment, I will say that we are blissfully pretty much limited to one country. I think.
Capital One operates in one country, but we do have a lot of
So right, we still do have a decent amount of regulation that goes on behind the scenes to get all of these things done. I can't make any guarantees except that this is, I think, one of the things that sets us perhaps somewhat unique among the crowd, that all of the stuff that we do with Flink does need this regulatory back end. And so there is a lot of recording data going in and out. And I think the main story is just that you have to get used to the ability to not only just calculate the result of a window, but you need to keep passing all of the data all the way through so that you can create a trackable record of what came in and what came out so that somebody can go and audit it later. For the time being, most of our regulation is based around auditability rather than anything more complex. I'm not sure if that fully addresses
so it's
what
mostly you just have to capture it, with regards to like know your customer or regulations like that.
Yeah,
for the most part, that's only really applied to us end to end. We haven't really gotten into anything, I think, in the middle.
Yeah, I mean, we still tokenize most of our sensitive data, even within our pipeline. So,
thank you.
Any more questions? All right, then let's thank the speakers.
Thank you.
Thank you.